Law of Relativity. The Law of Relativity was put forth by Albert Einstein. The theory is made up of two parts: the Special Theory of Relativity, which he published in 1905, and the General Theory of Relativity, which was published in 1916. According to Einstein, the Law of Relativity states that all of motion must be relatively defined, taking a frame of reference. This shows that space and time are relative rather than just an absolute concept. In the theories put forth by Einstein, he talks about the presence of black holes, gravitational waves, and the possibility of time travel. He talks about how the world came into being and what role the Big Bang had in it. His laws of relativity revolutionized physics completely. The Law of Relativity is a revolutionary theory that has changed how physics looks today. The Law of Relativity was published by Albert Einstein. The law is divided into two theories. The first theory is Special Relativity, which was formulated and published in 1905. It took Einstein over a decade to publish the General Theory of Relativity. Einstein's studies correlate with work done by Galileo and Newton. However, his groundbreaking theories are solely responsible for identifying some of the physics' most devastating consequences, which are still followed to date. The theory of special relativity talks about objects in uniform motion. The theory quite essentially explains the relationship between time and space. This theory has two main postulates by which it functions. This is the principle of invariant light and the principle of relativity. This entire theory's main concept is how reference frames and relative motion works, and how it affects an observer's ability to see an event. Some of the major consequences of special relativity theory are time dilation, length contraction, relativistic mass, the maximum speed is infinite, relativity of simultaneity, and mass-energy equivalence. The theory is mostly used to calculate events happening in different reference frames at a time. The Special Theory of Relativity was an upgrade to the theory of special relativity. However, the theory was rarely used in the early days. It was used as a means to make minor adjustments to certain theories and for experimental purposes. Also, the mathematics used in these laws was difficult and could only be understood and used by a few people. This changed as time went by, and people started finding answers and solutions using this theory. The General Theory of Relativity deals with accelerating objects and talks about how gravity affects them. It discusses how forces of gravity, along with inertial forces, are similar in nature. Einstein discussed how gravitational waves are caused by some of the most energetic and violent processes in the universe, caused by big objects like black holes and neurons. They are orbiting each other, would disrupt space-time, leading the waves to move in all directions away from the source. A few prominent consequences of the General Theory of Relativity are gravitational time dilation, frame dragging, precession, metric expansion of space, and light deflection. Some of these consequences have taken place right at the instance, while the latter had to be researched years at a time to get a conclusive outcome. In his theory of general relativity, Einstein speculates the presence of time travel and the existence of wormholes. This, however, is not possible in the world we know today. But if there are some unforeseen circumstances, there are chances these events may come to fruition. He also talks about the presence of black holes long before anyone was aware of its existence. This theory, put forth by Einstein, portrays the best methods to predict gravitational interactions. Like with everything, there are some drawbacks to this theory. One of the most prominent is science's inability to develop quantum theories that can help explore this theory fully. Humans have used Einstein's law of relativity to produce electronic gadgets, separate gold from other metals, find out about the origination of fossils, used it to generate electricity, and, most importantly, set up a global positioning system, GPS. Most of our day-to-day products are obtained from manufacturing processes. Manufacturing wouldn't be possible if Einstein's law of relativity didn't exist. In simple words, Einstein is one of the reasons for humans enjoying a luxurious life. Principle of the Law of Relativity. The Law of Relativity, or the Theory of Relativity, states that all motion must be relatively defined taking a frame of reference. This shows that space and time are relative, rather than just an absolute concept. The Law of Relativity was put together by Albert Einstein. The theory is also referred to as two theories, namely the Special Theory of Relativity of 1905 and the General Theory of Relativity of 1916. The theory of relativity, along with quantum theory, have been the main pillars of modern physics. In 1632, the theory of relativity was studied by Galileo. Galileo stated that the law of physics is the same in uniform motion for all bodies. The same theory was studied by Isaac Newton in the 17th century. Newton, with his laws of motion, concluded that if laws of motion were placed in one inertial frame, then they will also be held in a reference frame, which is moving at constant velocity with reference to the first frame. Albert Einstein's theories had the same reference point as Newton's and Galileo's studies. However, his theories of the speed of light, the equivalence of acceleration and gravity, and the structure of space and time set the parameters of modern-day physics. His groundbreaking theories are solely responsible for identifying some of the physics' most devastating consequences. These include the existence of black holes, wormholes, dilation of time, the bending of light, and the contraction of length mass-energy equivalence. By the 1920s, scientists and other physicists accepted and started using the principle of special relativity. It became an important tool for researchers and experimentalists in quantum physics, atomic physics, and nuclear physics. The principle of general relativity was, however, less used, as it could only be used to make minor adjustments to certain theories and for experimental purposes. The mathematics used in these laws was difficult and could only be understood and used by a few people. However, around 1960, it became quite influential and changed the face of physics and astrology. After so much experimentation and testing, Einstein's theories were quite famous, and even today are still the most important contributions by a man to science and the world. Einstein proved that Newton's three laws of motion were partially correct, and that the law of gravitation put forth by Newton was not totally correct as previously proved, as it broke down in the presence of strong gravitational fields. His theories explained some weird phenomena, like how astronauts age slower than other people on Earth, and how solid objects could change their shapes. This theory helped scientists and physicists gain a different perspective on time and space. Special Theory of Relativity. Einstein formulated the Special Theory of Relativity in a paper entitled On the Electrodynamics of Moving Bodies in 1905. This theory dealt with objects in uniform motion. This basically talks about the relationship between time and space. In its initial years before Einstein formulated the theory of general relativity, special relativity was called restricted relativity. After learning that Newton mechanics don't correlate with luminiferous ether and Maxwell's equation of electromagnetism, Einstein was quick to develop the special relativity theory. He devised two postulates related to the law of special relativity. 1. Laws that physics uses are identical when considered in a non-accelerating frame, which is taken as a reference. This is known as the principle of relativity. 2. The principle of invariant light speed states that when light moves through a vacuum, the speed of light is similar for all observers, and it doesn't depend on the source of light or the motion the observer sees it. The role of reference frames and relative motion. A reference frame in this theory is a stationary object in space that is not accelerating or undergoing any motion. The position of these reference frames is measured using the three spatial axes. These reference frames make use of a clock, which helps in keeping track of time in each event. The occurrence of an event can be any place in space concerning the reference frame. During this event, light is used to measure the event's longevity, as the speed of light is constant. The theory mostly used to calculate events happening in different reference frames at a time. The equations used to calculate these frames are called transformation equations. Consequences of the Special Theory of Relativity. This theory of Einstein is better suited to cope with experiments related to classical mechanics. The theory has many consequences that are experimentally verified. Some of the major ones are time dilation, length contraction, relativistic mass, the maximum speed is infinite, relativity of simultaneity, and mass-energy equivalence. Time dilation. Time dilation is a special type of relativity that talks about the slowing down of a clock which is seen by the observer. In theory, the observer is in relative motion with the clock. When talking about special relativity, the observer who is not accelerating has an idea of which events are simultaneously taking place, considering a given event. Consider a different observer who is in relative motion with the first observer. The second observer will not agree with the first observer with regards to the events occurring simultaneously together. Neither of the observers is wrong, but this only concludes that each event's timing depends on the observer's perspective and shows the notion of dependence in special relativity. To find out about simultaneity, it is necessary to compare the clocks carried by two separate individuals. The first observer, when he takes a look at the second observer, he will conclude that the second observer clock runs slow. Similarly, if the second observer observes the first person's clock, he will conclude that the first person's watch is slow. This shows that each observer considers each watch relative to him runs slower than his own watch. Special relativity also encompasses a phenomenon called the twin paradox. Consider two twins who are carrying a clock. One twin departs to space, while the other twin is an inertial observer. When they meet again, the clock of the twin who went to space will be smaller than the other, and he will age less than the inertial observer. The effect of time dilation has been confirmed by observations of increased lifespan seen in elementary particles that are traveling by nearly the speed of light. Length contraction. Length contraction is another phenomenon of relativity. This phenomenon talks about how the length of an object measured while it is in a state of motion is smaller than its length when it is measured at rest. This is not due to the fact it has faulty observations or errors in measurement. The object in its stationary frame is contracted in length. The speed of the object to the observer directly contradicts the length of the object. The contraction is realistic only when a moving object moves at relativistic speeds, or a speed that is close to the speed of light. It is important to note that contractions are only visible if it is in the dimensions of the object's movement. E.g., consider an object to be moving horizontally. The horizontal portion of the object will be contracted, and the height of the object will not show any contraction. Mass-energy equivalence. The principle of mass-energy equivalence is important in different aspects of physics. This includes some important fields such as particle and nuclear physics. Generally, in physics, all mass is an energy form. When this mass is in a resting phase, the mass and energy are similar and differ only by a constant. This is described in Einstein's famous formula, E equals mc squared. According to the formula proposed by Einstein, E stands for a particle at rest, m stands for the mass of the object, and c squared is the light's speed. The formula implies that a small amount of mass correlates with a large amount of energy, which doesn't depend on how the matter is made. Invariant mass is also known as rest mass, is observed when the system is at rest. This invariant mass is independent of any momentum, even when it is pressured by extreme speeds which are close to the speed of light. Maximum speed is infinite. This theory states that the speed of light travels fastest. No other message, action, or object can move faster than it. Though speed is mostly calculated and associated with light, it can also be used to calculate the speed of certain particles, gravitational waves, and electromagnetic radiation as it travels through a vacuum. In 1905, Einstein studied the speed of light, and he was able to conclude that when light travels through a vacuum, it is independent of the motion of the observer and the wave source. Previously, it wasn't easy to measure the one-way speed of light without knowing how to synchronize the clocks and the detector at the source. However, Einstein could calculate the speed of light by synchronizing different clocks at different places by sending signals. This ensured that the two-way speed of light became equal to the one-way speed of light. One of the most important features of the special theory of relativity is the fact that Einstein replaced the existing Galilean transformations with the Lorentz transformations. The law was able to explain the fact that time and space are defined together and called space-time. When inclined that events that occur simultaneously can be seen differently from one observer to the other. The theory is special and approximates general relativity as it only applies to places when the space-time is flat and can only be encompassed in conditions where the gravitational fields are weak and have conditions similar to free fall. Relativity of Simultaneity. This is another theory of relativity. In this theory, Einstein states that two events occurring simultaneously to an observer may not be the same for another observer when the observers are in relative motion with each other. Relativistic Mass. Relativistic mass in the law of relativity can be invariant mass, which is in a resting place, which is similar for all observers who are observing it in its reference frame, while relativistic mass, which is totally dependent on the speed of movement of the observer. General Theory of Relativity. The General Theory of Relativity was developed between the years 1907 and 1915 by Einstein. It was published in 1916. According to Einstein, this was an upgrade on special relativity that he put forth a decade ago. The General Theory of Relativity deals with accelerating objects and concepts pertaining to gravity. During the early phases, this theory was not taken seriously by many scientists, but as time went by, it became an influential block in how physics, and especially how studies on gravitations, took shape. Other theories explain how gravitation works, but the General Theory of Relativity is quite simple to understand and very easy to apply. Certain principles and predictions of general theory are radically different from classical physics. The Special Theory of Relativity helps in establishing a link between time and space. However, the General Theory of Relativity discusses the interactions between space-time. The universe is made up of 3 dimensions, or 3D, and has a 4th dimension in the form of time, and a combination of the 4 make up space-time and matter. Equivalence Principle. The equivalence principle in physics states that the forces of gravity, along with inertial forces, are similar in nature and often difficult to identify when together. According to Einstein, all objects falling from the sky are due to the influence of gravity. It is difficult to identify whether these objects falling down are in an accelerated frame or an unaccelerated frame. One important statement present in Einstein's General Theory of Relativity is that an object moves in constant velocity unless it is acted upon by force. Now, if the difference between an object falling down in a gravitational field and moving in a constant velocity cannot be distinguished, then it can be concluded that they are the same thing. Consider a light passing through a big object. Here, the path of light bends away due to the forces of gravitation applying pressure on it. This event can be measured even when there is a solar eclipse taking place. During a solar eclipse, stars behind the sun can be observed as the light is bent around a curved path. Gravitational waves. Gravitational waves are caused by some of the most energetic and violent processes in the universe. These waves are ripples present in space-time, which travel at the speed of light. In his theory of general relativity, Einstein stated that big objects like black holes and neurons that are orbiting each other would disrupt space-time, leading the waves to move in all directions away from the source. This would lead to the formation of cosmic ripples that travel at the speed of light. They carry information on how they originated and also how gravity works. Gravitational waves are mostly formed when two massive black holes collide, or when big stars explode at the end of their life, and when neutron stars collide. These waves are also caused due to the rotation of certain neutron stars that are not in the shape of a perfect sphere, and certain material left due to the Big Bang's radiations. Einstein predicted the existence of these gravitation waves in 1916, but it was not proved to be correct until 1974. These conclusions were mostly derived from mathematical solutions rather than by direct contact. It was only in 2015 the Interferometer Gravitational Wave Observatory, LIGO, physically observed these gravitational waves. LIGO physically sensed this effect when they felt black holes colliding 1.3 million light-years away. This discovery by LIGO will go down as the greatest achievement in science by mankind. Consequences of the General Theory of Relativity. A few prominent consequences of the General Theory of Relativity are gravitational time dilation, frame dragging, precession, metric expansion of space, and light deflection. Some of these consequences followed quite quickly and naturally, while some have taken years of research to get conclusive answers. Gravitational time dilation. The theory of gravitational time dilation is the time that passes by as two separate events occur and are measured by observers situated at suitable distances from gravitating mass. In simple words, time runs slower when an object is closer to a bigger surface or higher gravitational potential. E.g., time will run slower for humans on the surface of the Earth compared to someone on the orbit of the Earth. Now, let us consider a person X who is close to strong gravity and a person Y who is close to weak gravity. When X observes his clock, it will run normally. At the same time, when he observes the clock of person Y, it will run faster. When person Y observes his clock, it will run normally. But when he observes the clock of person X, he will see it running slowly. Nothing is wrong with the clock, but time is only speeding and slowing down because of the way time and space are wrapped by mass. This has played an influential role in developing global positioning systems, GPS. Frame dragging. This effect is caused by space-time and caused due to unstable distribution of mass. Rotating masses are known to drag space-time around them. Precession. In precession, when the axis of a rotating body rotates on a second axis, then the body is said to be moving in the second axis. In physics, this is also called nutation. In astronomy, this phenomenon is observed when there are slow changes in the astronomical body's rotation. The metric expansion of space. The metric expansion of space is a key parameter and helps in understanding the universe a little better. In this theory, space-time is described by an object which changes over time. It shows how spatial dimensions can stretch or grow as and when the universe grows older. It forms the basis of the Big Bang theory. The universe was formed 13.7 million years ago in a hot and dense state. This expansion of space is completely different from other expansions seen in nature. Light deflection. According to the theory of general relativity, light will follow the direction of the curvature as it passes close to a star. Initially, the effects were observed when distant light was observed being deflected when it passed from the Sun. Applications in astrophysics. Formation of black holes and other celestial objects. In certain events, when the mass of an object becomes larger than its radius, it results in the formation of a region that literally has nothing, and even light cannot escape. This region, according to the theory of general relativity, is called a black hole. The black hole usually has at least a few million to trillion solar masses encompassed in the center. It is believed that these black holes play a huge role in the formation of galaxies and other celestial structures in the universe. Researchers today are looking out for black holes, as this has a strong signal of gravitational waves which can be reached easily from the Earth. Gravitational Lensing. Gravitational lensing is a phenomenon which bends the light emitted from distant galaxies as it passes massive objects in the universe as a result of gravitational pull. Strong gravitational lensing can result in the formation of multiple galaxy images, known as Einstein's ring, while weak gravitational lensing will produce a weak or distorted image of these galaxies, better known as arcs. Over the years, this gravitational lensing has been used as a tool for observational astronomy. It has been used to observe dark matter. It is thought to consist of 85% of the total matter in the universe, and has been used as natural telescopes for observing distant galaxies. Time travel. In some parts of Einstein's equations, there shows a presence of closed time-like curves that show certain loops in time. These situations are, however, quite unlikely to occur, and would require extreme conditions to come into fruition. It is up for debate whether future physics will completely eliminate any claims for time travel. Wormholes. Wormholes are another mathematical presentation of Einstein's general law of relativity. Wormholes are shortcuts for long passages across space-time to different parts of the universe. However, wormholes are subjected to collapse due to high radiation and contact with dangerous matter. To date, nobody has been able to prove the existence of wormholes. There might be instances where wormholes may be formed, like the mouth of each black hole. But a dying star will not create a wormhole, so this theory is also not concrete proof of the existence of wormholes. Gravitational wave astronomy is an upcoming field of observational astronomy that uses gravitational waves to find out about events such as the formation of black holes, observations of neutron stars, and certain events like supernovas, which were binding figures in the formation of the universe after the Big Bang. Einstein and Newton's ideas about gravity are quite similar until the gravitational field's strength comes into the picture. The main difference between Einstein's gravitation and Newton's gravitation was that Newton considered that objects in the universe fall as they are pulled by the Earth's gravitational forces piles. On the other hand, Einstein concluded that these objects, along with the Earth, move along a curved space-time. The mass and energy of these objects have induced this curvature. Einstein's theory of general relativity is the best method possible to predict gravitational interactions. Some indications suggest that the theory is incomplete, and there are a lot of things yet to be discovered. The main problem is that there are no quantum theories capable of backing this theory and putting it to use to its full potential. Scientists today are trying their level best to develop a quantum theory version of general relativity. Applications of Einstein's theory of relativity in our lives. According to Einstein, when somebody sits near a girl for hours at a time, it only looks like a few minutes. But if that person is sitting near the stove for a few minutes, that would seem like hours. This is what relativity is. The law may be a complex mathematical problem to most people, but it explains certain things we do in our day-to-day lives. Here are a few examples of how Einstein's laws of relativity have helped everybody today. Electromagnets. Electromagnets, or magnetism, works because of relativity. And the fact that there is electricity is due to the presence of the laws of relativity. An electric current is produced when a loop of wire moves through a magnetic field. Current is produced in the magnetic field as the protons and neutrons present in the wire are affected by the magnetic field's movement. But if the loop of wire is at rest, and the protons and electrons in the wire are also at rest, then the magnetic field shouldn't be able to affect them. However, this is not the case, and current continues flowing through the wire. This explains that there is nothing called a privilege frame of reference. The same set of consequences can be seen in electromagnets as well. When a direct current, DC, flows through wire, protons and neutrons are seen moving through the wire. The wire will be electrically neutral, containing no positive or negative charge. When there is an identical wire near the existing wire, the electrons present in the first wire will consider the electrons in the second wire to be motionless. They will assume that the current movement is in the same direction and has the same strength. However, from the electron's point of view, electrons' movement is in both the wires. The wires appear to be closely spaced due to the realistic length contraction. This will result in the presence of a more positive charge and less negative charge. The wires will repel from each other as like charges repel from each other. The opposite effect can be seen if the current is reversed on one of the wires. Global Positioning Systems, GPS. GPS has to take into account the realistic efforts if it has to function properly. Satellites don't travel as fast as light, but they move fast enough to track movement. If that weren't the case, people would be traveling and going to the wrong destinations due to the system's inaccuracy. GPS satellites send information and signals to ground stations. These GPS carriers experience higher acceleration as compared to other satellites in the orbit. There is time dilation taking place every 4 milliseconds every day as the satellites are above 12,000 miles above the Earth and move at speeds of over 6,000 miles every hour. If gravity is taken into account, then a total of 7 milliseconds are taken away each day. Satellites use clocks that help to detect time accurately to a few billionths of a nanosecond. If GPS wouldn't have accounted for this law, then the directions would be inaccurate. All shiny metals are not gold. Light is mostly emitted with electrons, which are either absorbed or re-emitted due to the electron's movement within orbitals. This is the reason why most metals look shiny. Gold, however, is a heavy metal, and its electrons move as fast as the speed of light. This vindicates their mass to increase and their lengths to become short due to the law of relativity. The electrons in gold have a similar energy to that of the outer shells, such as the wavelengths which are absorbed by it are longer. This results in the absorption of more blue light in the blue end of the spectrum. As a result of all this, the light which is reflected from gold is yellow and has little to no blue or violet. The spectrum of yellow has a bigger wavelength than blue. Effects of relativity on gold. Relativity affects gold in one way or the other. The ability of gold to react or not react with other materials depends very much on relativity. According to the model proposed by Bohr, gold only has one atom in its outer shell. It should be highly reactive like calcium and lithium, but it is not. This is because heavier electrons of gold are held closer to the atomic nucleus. This ensures that other atoms don't affect these electrons, and they are placed close to other electrons close to the nucleus. This can also be a reason to why gold doesn't corrode easily like other metals. Mercury. Like gold, Mercury has heavy atoms, so they are enclosed very closely to the atomic nucleus. This protects it against influence from other elements. However, unlike gold, the bonds between the atoms of mercury are weak. This in turn facilitates the melting of mercury at lower temperatures as it turns into liquid. Old TV sets. In the early 2000s, long before plasma TVs came into fruition, TVs and monitors were made using cathode ray tubes. Cathode rays fire electrons with the help of a big magnet on a phosphor surface. A lighted pixel is formed when an electron hits the back of the screen. The electrons fired on the screen make sure that the screen moves at 30% of the light's speed. When manufacturers produced these TV sets, they referred to relativity law and shaped the magnets in that manner. These TVs may be slowly dying out today, but its references are still used in other places. Light. If we would have assumed Newton's explanation about light, then the world today would have been completely different. According to Newton, there exists a rest frame in the universe. If this was true, then the existence of light wouldn't exist. In the absence of light, magnetism would also not exist. This is because relativity requires the electromagnetic field to work at a finite speed and not in an instant. If relativity wouldn't control or enforce these certain requirements, then the communications via these electric fields would be communicated instantly, and as such electromagnetic fields, magnetism and light would not necessarily be required. Sunlight and nuclear power. From a nuclear power plant to a small bulb at your home, if the principle of relativity was not defined by Einstein, the presence of these features may not have been possible. Electronic equipment. The identification of photons led to the development of all electronic equipment we use today. Einstein's ideas about quantum effects paved the way for developing cellular telephones, alarms, automatic opening doors in supermarkets, and many more inventions. Einstein's work on photoelectric and photovoltaic effects laid the foundations for developing DVD players and lasers. Without the work done by Einstein, the existence of computers and semiconductors wouldn't be possible. Carbon dating. Old fossils can be dated, all thanks to Einstein. His famous theory of E equals mc squared describes how mass and energy are interrelated. By checking the atoms for degradation in the nuclei of organic material, we can tell how long the fossil existed in the world. Daily life. Most of our day-to-day products are part of the manufacturing processes. If Einstein's work on atomic theory wouldn't have worked, then all of this wouldn't exist, and our life wouldn't be so luxurious. Existence of the human species. Before the existence of the Sun, most masses in the solar system were formed by a supernova. We are all creating this star along with heavier atoms, which are created within the atoms of the supernova. Supernovas usually occur when quantum effects are overcome by relativity. This results in the star's explosion into the core and subsequently creating elements that are heavier than iron. All the heavy metals that are present on the Earth today are due to this phenomenon. A century later, the Law of Relativity, published by Einstein, remains a very influential piece of evidence on how physics has evolved today. The General Theory of Relativity especially has completely changed physics. Einstein's theory predicted the existence of black holes years before there was any evidence, and before it was known to anyone. He also suggested that the world came to fruition because of the Big Bang theory. Einstein himself didn't believe both these theories, but as scientists studied more about them, it was clear that Einstein was correct. The theory of general relativity also predicted the possibilities of time travel. However, this could all be speculations, unless future physics predicts the same to be true. He also spoke about the fact that there exist chances of wormholes that are tunnels through space-time. It is important to note that these ideas don't actually work according to our universe, but certain special circumstances may facilitate such events to occur. In the meantime, these ideas are firmly science fiction and have been used in many movies. Einstein also predicted the existence of gravitational waves, caused when big accelerating objects collide, creating ripples in space. Einstein predicted these gravitation waves' existence in 1916, but its existence was only accepted in 1974, and over time scientists have studied about these effects thoroughly and precisely. The conclusions derived by the scientists were mathematical solutions rather than through direct contact. It was only in 2015 the Interferometer Gravitational Wave Observatory, LIGO, physically observed these gravitational waves. LIGO physically sensed this effect when they felt black holes colliding 1.3 million light-years away. This discovery by LIGO will go down as the greatest achievement in science by mankind. This has left the door wide open to see how the Earth was formed and how the Big Bang Theory played a part of it. The application of Einstein's theories has helped man develop electronic gadgets, conduct carbon tracing of century-old fossils, and create GPS, which makes getting to our destinations quite easy. His theories also helped separate gold from other metals and have enabled us to have electricity in our homes and workplaces. The works of Einstein's, especially the theory of relativity, is quite ingenious. These theories have far-fetching applications and have helped in creating inventions which have enabled man to live a luxurious life in the 21st century.